we're going to do separable equations. Again, there's nothing new. You probably did this already. And then if we have time today, certainly by Wednesday, we're going to do the first order linear equation. And what's interesting about that is that I'm going to show you that there's a closed form solution for that, for any first order linear equation. But before we do that, let me go and give you an example of an autonomous equation. Suppose I have the equation dy dx is equal to y minus 1 squared, okay? And I want to satisfy the initial condition, y of 0 equals -1. Now, of course, if you separate variables, you can do this analytically. Again, that's the next topic. But let's just play with this machinery that we've developed for autonomous equations. Okay, we're in the xy plane, right? In this equation, dy dx equals y minus 1 squared only has one equilibrium solution. It's y equal to 1, right? That's it. Okay. And of course, we could easily graph what it looks like above y equals 1 and below y equals -1. But since we're just in the curve that goes through 0, -1, okay, let me just put a little dot over there, okay? That's 0, -1, okay? We're interested in the solution, obviously, that lies below the equilibrium solution, y equals 1. But in any case, the slope is always positive, okay? So we go through that point with a positive slope, okay? And we know that it has to stay in that strip, a positive slope, but it can't cross that equilibrium. So it's asymptotic to y equals 1. What happens over here, though, is not so clear, right? Does it keep on going and decreasing? Or maybe there's some type of asymptote that it approaches, okay? And remember, I wanted to explain that to you, that with this machinery we developed analyzing the autonomous equation through equilibrium, you really can't tell in this case what happens as x goes to -infinity. Certainly as x goes to +infinity, there's no question in asymptotes to y equals 1 from below. It comes out that you actually can solve this analytically, and the solution comes out to be 1 minus 1 over x plus a half. You should at least verify that, if not derive it, okay? So therefore, there's an asymptote, what? At x equals -1/2. Draw that in over here. This is x equals -1/2, okay? Which means that if we continue and we fall, we never cross that asymptote. Now we become asymptotic here. Okay? So it goes like that. Now, of course, this is not violating anything that we said before. Okay, we know that as we go in the direction of -x, we'll go to -infinity on y. What we do not know is if that happened with a vertical asymptote, or maybe it just keeps going and going across here and there is no asymptote. But the analytical solution, obviously, at x equals -1/2, you can go to -infinity. Okay? Since we have that equation up there, let's just do a related one. I'm just going to change the initial condition. Okay? Again, it's going to be dy dx. So we'll go through 0, -1 is equal to y minus 1 squared. Now let me take an initial condition on the other side of the equilibrium. Let's say y of 0 is equal to 2. Okay. Well, we can do the same thing. Of course, we have, here's our xy plane. Okay, we've got that, the same thing. We've got the equilibrium solution, y equals 1, right? That doesn't change, right? But now we want to go through the point 0, 2, right? Let's say that's around over here, 0, 2, right? Nothing's changed as far as the slope goes. The slope must always be positive, except, right, because we're above y equals 1. So it increases as we go from the left to the right. 0, 2.
It should be
Yeah,
above.
be above. Yeah, something like that, right? Thanks. So here's our y equals 1. Right, here's our point 0, 2. Okay, it has a positive slope, right? So definitely, as we go to the left, we're going to asymptote to y equals 1 from above, right? Because it has a positive slope, so going to the left, it falls off. And then as we go to the right, we know it's going to go to +infinity, but again, you know, what's going to happen over here? Is it going to go to +infinity as x goes to infinity? or is it going to have an asymptote again? And in this case, you can easily verify that it has an analytical solution, y equals 1 equals 1 minus 1 over x minus 1. So clearly at the point x equals 1 now, we have a vertical asymptote. I'll just draw that over here. Right, this is x equal to 1. And therefore what happens over here, I'm sorry about that, it's not that great. We come over here and we increase and we increase and we asymptote like that. Right? We have that vertical asymptote x equal to 1. Okay? I just wanted to give these two examples to show you that indeed there are times when you just can't assume that, oh, it's increasing slope over here, so it just keeps going up and up and up. You may have a situation like this. Okay? That you cannot get from the theory of autonomous equations. You need some more information. Now again, you say, gee, the only way around that is get the analytical solution. But again, if you're doing a physical problem, many times you know a priori that there's an asymptote over there because of some physical condition. So therefore, if you knew that, plus the fact that you can just sketch in the equilibrium solutions, you would have the whole solution, qualitatively at least, you'd have the whole solution there. Okay, and then one more example over here, which is, okay, just untold models like population growth. Okay. Yeah, let me just get the, yeah, sure.
So would a materials breaking point be like an asymptote in this kind of a
those usually aren't governed by autonomous equations.
Okay.
A better example would be, I'm trying to think of a physical thing that you could have. Like an elasticity, where you'd have a crack propagating through materials, and that would have this type of behavior. Okay, this one is given in all books. It's called a population model. Okay, and again, well, I think I'm going to press you with this. I'm going to do it just your autonomous theory, and then I'm going to actually show you the analytical solution. And we look at the analytical solution, very nice, but there's no way of knowing from looking at it what the heck is going on. Okay, you'd have to put it onto a computer. Okay, so this is a good illustration of nothing else. dPdt, P is like a population, I think, is P parentheses A minus BP. And the book has a whole discussion on this. You probably learned in your elementary biology courses of how the population of bacteria grow proportional to the number, or this rabbit sometimes they use, right? So that will be dPdt equals AP, okay, where A is a positive constant, saying that it grows according to the number, proportional to the number. But then there's this problem of competition for food and survival type stuff. So epidemiologists come along with a little more sophisticated model where they put like a negative feedback on that. The people in control call it negative feedback. And important here is that the parameters A and B are both positive. Okay? But we don't, all saying is that they're positive. Let me give you the numerical values for these. Okay? And you say, gee, how the heck am I getting information about that? It's pretty general. Okay? And let's just go through. First of all, does everybody see it's an equilibrium? I mean, it's an autonomous system, right? Because here the dependent variable is P, and the derivative is only a function of the dependent variable. Again, because of my experience, you have to get used to different symbols. It's not always dy dx, okay? So the dependent variable is P, and the definitional autonomous equation is that the derivative is independent, is only depending upon the dependent variable. The independent variable, in this case T, doesn't appear on the right-hand side. Okay. So we look at this, and now we have equilibrium solutions, right? Just set the right-hand side equal to 0. Okay, what are the two ones? P is equal to 0. Okay, so I'll just superimpose that over here. Right? That's supposed to be a straight line, believe it or not. Okay, and then we have what? When A minus BP equals 0, P is equal to A over B. What do I know? A to be a positive, so I'm just going to put it over here. I definitely know it's up here, right? So there's the equilibrium solution. P equals A over B. Okay. Now, usually we want to graph this in the entire PT plane. In this region, in this problem, there are three regions we have to worry about. Above the equilibrium solution, P equals A over B. Between the equilibrium solution, P equals A over B and P is equal to 0. And below, right? So let's just do each one in succession. Okay. Let's take a point. Suppose at T equal to 0, we're over here. Okay? We're greater than A over B. Okay? Remember, in each of these strips, the derivative is going to be either positive or negative. Okay? So, I think you can see over here, since P is greater than A over B, that means that BP is greater than A. That's negative and that's positive. So it's a negative, right? So it's just false. Okay? So it goes like this. Definitely there. And again, what happens over here? I don't know. Is there a vertical asymptote there? Does it go all the way? And actually, in the physical world, you know, kind of not interested in that because that's T negative anyway, okay? But, you know, if you want to just, you know, play a game, what happens when T goes negative, you know it goes like that. But there's no question that you get this equilibrium solution. As T goes to infinity, you approach the equilibrium A over B from above, provided your initial condition was over here, okay? So it's very interesting how the solution behaves for large time depending upon what your initial condition is. Everybody got that? Why that is negative? Right. Okay. Now let's do a point between here and here. It doesn't have to be the midpoint, I don't care, right? So that's basically what? My T equal to 0, my value of P is greater than 0 but less than A over B. So this factor is positive, right? But now, what happens over here? This should be positive also, right? Yeah, because what happens now is that P is less than A over B, BP is less than A. Let me just get the sign right over here. It has to be a positive slope. Yeah, because P is less than A over B. Okay, so here we have a positive slope, okay? So what's going to happen? We have to approach this, we increase, so we go like this, but we can't cross the other region, right? So that happens over there. Similarly, what happens now on the other side when T goes to minus infinity? We decrease, but we can't go to minus infinity, otherwise we'll cross this other equilibrium. So we know that happens over here as it goes like this. Okay? Asymptotes to that. So that's the solution for an initial value between A over B and 0. And finally, let's take a value of P down here. Okay? Let's see what happens over there. You get P is negative, right? P is negative, so that's negative, right? But then negative BP, B is positive, that's positive times negative, so that's going to be negative. So it just falls as we go to the right, right? Okay? And then what happens over here? It has to increase, but we are limited by that asymptote, right? That's something really nice. It shouldn't change concavity like that. It should just be, just draw it a little better than that. Okay? And again, we don't know what happens over here. Is there a vertical asymptote, or does it actually go to negative infinity with T going to plus infinity? But here, when you're in between these two equilibrium solutions, there's no ambiguity, of course, because it has to go to infinity, but it can't cross. Here it has to go to 0, and it can't cross. So it looks like that. So there's a pretty general equation. We never assumed any numerical values for A or B, but yet we can graph it, and we see that there are 3 critical conditions that you have. And what I encourage you to do is, play with some numerical values of A and B. Make A equal to 2, B equal to 3, and then use MATLAB's ODE solver that we did, and you'll see that if your initial condition happens to be bigger than A over B, your graph will go like that, and similarly for the other regions. Something which, if you didn't have this, analysis, you really wouldn't know, okay? And what's interesting about this, like I said, is that the character of the solution is critically dependent upon the initial condition, right? There's a big difference between this curve over here, right, and this one. And it's the same differential equation, right? All that changed was the initial condition. Okay. Okay, there's some terminology which, I just want to bring in because it's used a lot. It's just a classification of the different equilibriums as being stable, asymptotically stable, stuff like that. And unlike the book, I'm going to show this in 2 different ways because I think it's much easier to see these type of diagrams. But they call these phase diagrams. Okay? And usually, for example, on an exam, if I ask you to, typically I'll give you like an autonomous equation, and I'll say, graph the solution between all the equilibrium positions. Remember, I want to do all cases, Like in this case, we have 2 equilibriums, so you have to do above this, between here, and below. Okay? And then I'll ask you things like, is this stable or unstable? Okay, why is stability so important? Well, when you design control systems as an engineer, it's critical that the design be stable. What does that mean? Give you an example. Okay, you basically, a lot of people are involved with aircraft and design a control system that reacts to wind gusts or something. You know, you're in an airplane and you want to fly level flight at a constant speed, say for most of the trip, right? Except when you're descending and ascending. Okay, what happens? There's all types of disturbances on the space, on the aircraft, right? People move around. You know, some 300-pound guy goes to the other side. Thank God the thing doesn't turn over. Okay, or if there's a wind gust. Okay, and what happens is that the control system has instrumentation. It measures all these things like the attitude and the speed, or whatever, and the angular displacement, and then signals are sent to counteract that disturbance. So, for example, if a whole bunch of people run to this side of the plane, and now normally it would just go like this, right? It would roll, okay? Then the gyroscopes on board basically are commanded to spin up, so they give a torque the other way to balance that out. And what's critical about stability is the fact that nothing is perfect, okay? So if you design something based upon, well, if this was exactly 30 miles an hour and this thing was exactly spinning at so many RPM, the problem is that when we design real hardware, it's never perfect, and you have errors, okay? Now the problem is that if you have this autopilot designed for a nominal flight condition and there's disturbances in it, you want to make sure that it doesn't really take you off the desired equilibrium. In other words, small perturbations of the input shouldn't produce large changes in the solution. And you can see how this is critical over here. Something like this is a desirable thing, well, this thing is undesirable. And to do that, there's a little nomenclature that's involved, okay? And we'll just call this the stability of critical points. Okay? All these critical points, like here, P equals A over B, P equal to 0, or we call them equilibrium, stationary, right? All of them are classified according to their stability, okay? And the diagram that the book has is I'll draw two diagrams for you, okay? This is the stable condition. So they have like y equal to C, something like that, and you're looking in the neighborhood, and they